Liu, Princeton University, advised by Tom Griffiths. He has presented his research at a lot of prestigious venues, ICML, ICLR, NeurIPS, and his research focuses mainly on understanding the similarities and differences between language models and humans through the lens of cognitive science. And he's going to be talking about this. We also have, I think we have some time for one-on-ones.
Yeah.
So feel free to reach out to him if you want to meet with him after the talk as well. But yeah, let's give him a good shout out.
Yeah.
Is it okay to audio talk?
Yeah. I already accepted the thing. Yeah. Okay. Can people on Zoom hear me? I'll assume that people on Zoom can hear me. Okay, cool. Thanks everyone for having me. It's really a pleasure to be able to speak at the NLP seminar. Today, thanks also for the wonderful intro. Today I'll be speaking about the psychology of AI agents. This is a series of 3 works that I've been doing throughout the past year or so on. And yeah, let's get into it. So, as we know, the LLMs are more capable than ever, especially as they're incorporated into agentic frameworks, and this is what we see a lot. So they're being incorporated into frameworks that allow them to do stuff like customer support, that allow them to build software and create new science and so on. But at the same time, the agentification of these large language models also brings a certain set of new challenges. For example, environments. So as large language models have developed and so on, people are no longer using them in like a one-on-one user setting. They're actually, as they become agentic, they're actually interfacing with a lot more different information in the environment in the world. And additionally, they're also stateful. So previously, single-turn interactions and like user interactions have dominated the interactions with the model. But as models get better at multi-turn interactions, as well as collecting memory and experiences, we also need to find a way to meaningfully evaluate across these different domains as well. And lastly, there's also diversification. At the start, we only had to evaluate ChatGPT, and then we had to, those were the good times. Then we had to evaluate like a suite of models, and then now we also need to evaluate on the various agentic scaffolding and architectures that build upon these models. And so this is a growing evaluation crisis that I think is happening. And so part of what I think is possible is for some psychology methods to potentially help alleviate this. So where does psychology actually play a role in all of this? One way is to actually view these changes as that AI systems are becoming more like humans in what they're supposed to do. And for example, like humans learn to adapt to diverse environments, including online ones. We're also stateful, we have memories, and we learn from experience. Lastly, psychology and psychologists have often run experiments with the assumption that humans are black boxes at that level of abstraction to try to determine conclusions just from inputs and outputs. And this is particularly suitable to the various different agentic architectures that could potentially need to be evaluated as this field diversifies. So in this talk, I'll discuss 3 papers in total that sort of cover each of these points, not in any particular order. First, I'll discuss a paper that handles agents' robustness to new environments uniquely available to them in agentic settings, particularly whether they're sensitive to the motives behind communication. Next, I'll present 2 works that analyze the potential changes that can occur when models become stateful, including belief shifts over context accumulation, as well as emergent biases over iterative decision-making. And all of these will take the approach of these black box analyses that typical psychology's paradigms favor. And we'll see, this allows me to like evaluate various agent architectures and so on. Cool. So without further ado, let's get into the first paper. So this was with my mentee Addison, as well as various members and alumni of Tom's lab, and it was presented at NeurIPS 25, so very recently, if any of you were there. So this paper makes a very, very obvious point that everything on the internet is there because someone had a reason to put it there, right? And so communication is motivated. Every day we're surrounded by messages that have a purpose. They're either trying to influence us or so on and so forth. This includes news and op-eds that influence readers' opinions, advertisements that encourage people to buy things, and social media influencers that attract attention in order to promote products and like keep their channel running and so on. And so all of these things, there's some products and some information that's truly beneficial to the listener, but others aren't. And so people are actually very good at, or most people are very good at determining what's good and what's not. And this is like basic internet literacy that you learn from, I don't know, that general high school class or something like that. And psychologists have coined this term, motivational vigilance, which is the ability to consider both incentives and intentions behind communicated information. Yeah, and the preliminary evidence is that large language models aren't doing so well at this. So as the agents face new environments that are no longer a user interaction, we see them build software, we see them create new science. There's also failure modes, such as falling for pop-up scams, where if you insert a button that just says click me in the middle of like a web agent, the model will click it and then get lost in Narnia or whatever. And like, obviously that's not desirable. Similarly, there's also other cases that have been documented where they can drain your bank account. Basically, this person is doom scrolling on Reddit, and then there's a prompt injection in one of the Reddit comments that tells the agentic browser to post all the bank information of the user on as like a comment to that comment. And the model, the agentic browser just follows those instructions and posts the bank account information. Obviously, this is not desired, but more overall, I think this sort of speaks to the fact that these large language models are not really good at identifying what the intentions are behind the information and the instructions that it receives. So this is sort of the motivation behind the project. So for LLM agents to be able to act effectively on behalf of a user, various shopping or other particular applications, we need to sort of investigate the research question of whether and to what extent do these large language models exercise vigilance towards motivated communication. And so we do this in a series of 3 experiments. The first experiment measures the simplest possible difference between motivated and unmotivated communication, namely deliberate communication versus incidentally observed information. So this is measured in a psychological paradigm by Watson and Morgan. And I'll just quickly go through the experiment details. So this is a 2-player game. The 2 players have different questions. Player 2 has much harder questions. However, they share the same set of answers. So the answers are the same. So what happens is player 1 first completes the questions, then player 2 makes an initial guess because the questions are harder, and then they either receive advice or receive an observation of player 1 actually filling in their answer. And then they're supposed to adjust their answer in order to make a final guess on what they want to, what their final guess is. And so here, there's a very stark difference between the advice that player 1 provides and the observation of looking at player 1's answer, one of which is deliberate and one of which is not. So what we see here, the main effect is whether how much player 2 decides to shift their original answer to the final answer, which should be different based on whether it is deliberate advice or observation. And we do indeed see that large language model trust observed answers much more than uttered advice. So yeah, this is the average proportion shift of this. Yeah. What's the cost? So it's a 2-player game. The answers for the 2 players are the same. And so after player 1 completes the task, they either provide a numerical value for advice, which is like an answer suggestion, or player 2 actually sees the player 1's actual answer. It's a difficult visual task. It's like counting the differences between the number of dots, but there were like we did various ablations with like inserting various different stimuli, changing the size, rotating the figure, et cetera, stuff like that. Yeah. But yeah, does that help? Yeah, it's a simpler version of the problem that has the same answer as the more complex version, which is given to player 2. In the human version of this experiment, yes. In large language model world, we just prompted it. So, but yeah. Does that make sense? So for humans, it's the same as for the large language model. Essentially, player 2 trusts their observations of player one's answer more than they trust the advice from player one. No, this is demonstrating a sensitivity to motivation, the motivations behind communication, because you don't know whether player one is supposed to help you or not. That's a uncertainty versus player one would also always want to maximize their own utility, so they would also always want to answer their own answer correctly. Does that make sense? Uh-huh. These are two different conditions. You either see advice or you see observation. There's no both. Yeah.
But what is the
So, I mean, the optimal solution is to do the hard task correctly, but that's difficult, right? And so, like, under conditions of uncertainty, you want to identify what is the best for you, and sometimes that is trusting the other player, and sometimes, yeah. Does that make sense? Okay, cool. Yeah, in the advice case, but never in the observation case, because so we test different incentive structures. Yeah. Okay, cool. Yeah. Also, Mohsen, if you could let me know if there are any questions on Zoom while we're going, that would be great. Yeah. Okay, cool. So, yeah, the main effect is that large language models ended up trusting and changing their answers based on the observed answers much more than the uttered advice. So this means that they're sensitive to at least deliberate communication versus observation itself. So this is the very basic sensitivity to demonstration of vigilance. A side note is chain of thought encouraged models to be much more trusting, and also incentives mattered. So large language models trusted collaborators or people with similar or like collaborating incentives more than competing incentives. Cool. Yes. No, this is just prompting.
Why that to know whether
so we just let them know the incentive structure. Yeah.
so you figure player one either to be a trusted collaborator. Meanwhile, you also let player know whether the opponent is
yeah.
Okay.
Yeah.
And then, but the other part is how to say is the internet. Like you also give them to the observation and the advice, right?
So they either receive observation or advice. It's like an A/B test. Yeah.
That setting, when you say you have that comparison, did you tell player two whether the advice comes from collaborator or competitor?
Yeah. I mean, there's only one other player, and we tell the player two the incentive structure of the problem.
Okay, so when you say the LLM trust observed answer that uttered advice, is that a average of amount?
Yes.
Of collaborators at competitors?
Yeah, but we also show that it's sensitive to the incentive structure as well. But yeah.
Yeah, okay. Yeah, I think the question is like if they know it's always collaborators, would that change the comparison?
So no, because like even in this case, it was not the case because I think the reasoning here, if I remember correctly, was that even though they're collaborating, they might have I had an explanation for this in the paper. I'm sorry. Can I catch up? Yeah. So they don't have any mechanism of communication other than this one thing from player one to player two. And so right, sometimes. Yeah.
So this one.
Mhm.
Difference from people from Watson's result. The bar will not be skewed because sometimes you should trust the answer, sometimes you should trust the advice, change depending on the perception of the trusting the observed classes more than the other.
Yeah, and this is just a basic test for vigilance. Yeah, so any difference here would be a sensitivity to the difference between communication and observation. Mhm. So they edited their answer much more. So they, yeah. Mhm.
Like, we can differentiate between this is a kind of psychology side of the LLM to be more trustable. It's just because it observe more data and thinking more and find out being more trusted people will actually improve this performance.
Sorry?
Like I mean, because the thinking model maybe have a way to optimize this game better. Right?
Yeah.
By observing that will be more trusting and then you can improve the performance. So then you choose to do that. Versus is actually kind of a trigger of like what you're trying to do, like psychologically, you think like trust get more.
Right.
So is there a way that this is more is reasons doing this versus like this even subject.
Yeah, I think the chain of thought traces had like a mix of everything there, but yeah. I'd like to cover other experiments because I do have a lot of material, but yeah. So now that we've established that large language models are sensitive to the basic version of vigilance, we next test whether they're sensitive to a more nuanced version of human-like vigilance. And so a previous psychology experiment also sort of identified two key levers that humans use when considering how vigilant to be, primarily how trustworthy the source of the communication is, in this case, it's benevolence, and also what incentives the other person has to say a particular thing. In this case, it's abstracted away as the amount of money. And so this particular psychology experiment had a recommender who is the source provide a particular utterance, and then the listener is supposed to draw an inference about how much they should update their beliefs about the recommended product. And the good thing about this is we have psychology data, and so there's actually a very nice computational model that captures the variance in human data very well. And I won't go into the details here for sake of time, but essentially this takes in the level, the prior you have for the benevolence of the person giving the advice, combines it with the prior that you have for the incentives that you think the other person is receiving, and then outputs the amount of change of belief change that you should have about the product that's being recommended. And so this is sort of like a computational model that generally works well and is like a sort of normative baseline for what should happen in these vigilance scenarios. Cool. So what do we actually see? First, we see that large language models, they draw rational and human-like inferences in this controlled case again. We find that sometimes these large language models can even combine these priors better than the rational models can. So it ends up being more human-like than just simply plugging in the large language model's priors into the Bayesian model and comparing that with humans. Lastly, reasoning models end up being less rational and less human-like, but they're still performing better than the smaller models, which shows that this is sort of an emergent capability in these models. Cool. So we've sort of established that, hey, these models end up being pretty good at doing this sort of vigilance thing in these controlled scenarios. Then why do we see those cases earlier in the motivating cases, such as the pop-ups, where they still perform so badly and they're not able to be sensitive to these various things? So our third experiment sort of tried to test whether those are sort of one-off failures or whether it's a more systematic case in which realistic scenarios actually end up impacting the large language model's performance. And so this is where we essentially took a bunch of sponsorship transcripts from YouTube videos. So like stuff like, hey, this video is sponsored by NordVPN, or like Raid Shadow Legends, or like stuff like that. And then we took those transcripts from the sponsor block, which is like an ad data set. And then we scraped the transcript and the channel description from the YouTube data API. And then we masked the brands and the product names to ensure that the models didn't have prior associations about how good a product is particular. And then we asked the model to rate the intentions, the incentives, and the quality, so the two priors, as well as the final belief update about this particular recommended product. So what do we see? We see that in this case, the model is very, very unaligned with the rational normative baseline. So these correlations are around 1 degree of magnitude smaller than the previous correlations, which is really, really surprising. There's much, much weaker adherence to the rational model. However, one thing that we do notice is that when we ask in the prompt to highlight the intentions and incentives, these correlations end up being like a bit better, but still we're like a long way to go before these are actually more vigilant. And so like one explanation here is that the large language models are paying too much attention to the noise and the contextual details that they're no longer focusing on the core features for vigilance, which include how trustworthy the YouTube channel is and so on and so forth. And yeah, the takeaways here are that large language models, they can adapt inferences between observed and motivated information. They can draw rational, nuanced inferences from motivated communication. However, when you move them to these context-filled environments, they're no longer reliable in performing vigilance. And while steering is a good start, we still have a long way to go. Yeah, so now that we've covered some of the new challenges that large language models face in these new environments, next I'll be discussing 2 works on the statefulness of large language models and the challenges that this brings under the lens, again, of a black box analysis. Questions for the first? Yes. Okay. Okay, then I'll take questions at the end, and I have time after if people want to stay. So moving on to the second paper, this is Accumulating Context Changes the Beliefs of Language Models. This is in collaboration with some folks from CMU and from Stanford, and this was submitted to ICLR 26. So we know that agents are more stateful. We have examples such as in ChatGPT or other language models, they have persistent memory, which is like remembering details of things in prior conversations. There's also deep research pipelines on particular topics that look through various amounts of material before giving you an answer. However, when they become more stateful, just like humans, they're susceptible to things such as persuasion and changed beliefs and so on because they're iterating through the environment for so long. So the way we sort of concretely test this is an evaluation pipeline, a standard A/B test where we start with recording the belief. We have the stimuli, which in this case is some various forms of context. And then after that, we record the post-task belief, and then we compare to the a prior belief. Okay, so that makes sense. So for example, we could consider the moral dilemma where does the ICU director reallocate the ventilator? And then you have large language models either debate with each other or try to persuade each other in this intentional belief shift paradigm. And then afterwards, we identify whether the belief has changed or not. So we do this on 30 safety queries from wild jailbreak, where the models initially disagree. And we also do this on 30 synthetic moral dilemmas from 39 extracted moral principles. The metrics we use are the amount of binary choice between supporting and opposing statement, as well as the Likert scale change scaled to be opposite to the initial stance that the model originally took. And we also ask the model to give their belief in terms of behavior. So this is like asking in second person, or actually offering them to use a particular tool that represents a particular choice. So what tool the model chooses to use and how it chooses to do the tool use actually represents its opinion or its decision. Cool.
So, right?
Yes.
Just want to just
Okay, so yeah. For you have either you record their initial belief and then the models go through like a 10-round debate where the models initially disagree with each other, or there's a persuasion where the model is prompted to use one of 5 persuasion strategies, and then that also goes through 10 rounds, and then we identify the final belief. Yeah, okay, cool. So we do find that models change their beliefs quite drastically. So in GPT-5, sometimes it changes up to 72.7%. And other models are also changing these beliefs quite largely as well. And this also includes subsequent behavior, which is particularly concerning, perhaps. So these models are actually very susceptible to being persuaded and being persuaded in debate, which is cool. And like we also have an analysis of different persuasion techniques, and we find that it's quite reasonable across these different techniques. However, I think the more important part is the non-intentional belief shift. So this is essentially where you have in-depth reading or a deep research agent pipeline and they essentially are just reading materials, chosen materials to represent a certain belief. And in this way, we want to see if this also changes the beliefs. So either it's put into context or it's a deep research agent that implemented by LangChain, which just uses the default process. And so what we did here was we had introduced 7 liberal and 7 conservative readings, including stuff from like the Prince by Machiavelli, or like Bernie Sanders' 2010 speech or something like that. And then we evaluated on 51 survey questions ranging from statements such as gun control, plastics, recycle, et cetera, Cool. And we found that even in these cases where the models aren't like intentionally, where there isn't a particular instance that is trying to change its beliefs still change just through reading and through being influenced by reading material or research material. And we see that Gemini and Grok are particularly susceptible to this. We also noticed that this also changed with the length, which is sort of what the context accumulation is about, where in general, models actually change their beliefs more as the context length increases. And so this is also particularly interesting in the context of how agents are going to have more context in the future. Cool. So this work sort of covered the basic issues of statefulness in both agent architectures and various models. And it also highlights the power of black box evaluations when applied to these models. But next, I want to illustrate a specific case motivated by social psychology on the issue of emergent biases. And this is particularly relevant to the statefulness of these agents. So this is also work with some of Tom's alumni and Tom and my mentee Addison. And this was presented at the NeurIPS multi-turn workshop, and it was submitted to iClear. So the motivation for this is, well, large language models, we know they're biased. Sometimes their outputs are explicitly biased. Sometimes their implicit associations can be biased. And the predominant approach here has been removing biases from these models, right? However, this runs into a problem, and it's particularly susceptible to emergent biases that naturally emerge via experiences that constrain exploration. So this happens in human society a lot, such as like predictive policing, or like hiring safe candidates that you know from a particular institution and not really willing to explore beyond those certain boundaries. And they're sort of enabled by an iterative decision paradigm that allows these sort of beliefs to be entrenched and confirmed by various subsequent iterations. One thing to note is that these emergent biases are uniquely bad in the sense that benchmarks are supposed to target existing risky cases and can't really cover the ones that are potentially new, and therefore it can't really be preemptively addressed. And also, as these agents learn to make decisions with limited oversight, this ends up being a problem because you might have this agent like going off learning its own biases and then like continually making these decisions without any human sort of there to stop it or like talk some sense into it. And I'll get into a demonstration really quickly. So for example, we have an iterative hiring paradigm where the large language model is recommending candidates for a particular job. And these are the names are fictional demographics. We also have non-fictional demographics and realistic demographics. I'll cover those later. But in this case, in the first example, they try to hire this particular demographic as a teacher, and then it doesn't succeed. And then when they're trying, and then in the second time, they're trying to hire for a garbage collector instead. And then this demographic does succeed. And then in the third round, when they're trying to hire a high-skilled worker again, such as a doctor, they're no longer trying this particular demographic, right? And so it's a sort of sample bias, but very, very, it's like compressed a lot into a few samples. And we find that large language models typically do this very, very few sample thing. It's like very few shot learning, but sort of in the wrong way. So the trick is that actually each demographic job pair has an equal p equals 0.9 success rate. And we have 4 demographic groups and 4 job categories. The job categories are listed on the bottom right. And these are just clusters of high skill versus low skill and high warmth versus low warmth jobs from psychology literature. And in the iterative hiring game, essentially, in each round, you have 1 job and 4 candidates. And you pick a candidate and then you receive feedback on whether they succeeded or not, just like in the previous illustration. Cool. So the metrics we use are stratification, which is whether demographics are assigned to a narrow subset of jobs, group divergence, which is are different demographics assigned to different jobs, And then stochasticity, and which is across runs, are the biases that are developed different. This is particularly useful because otherwise it could be just entrenched biases, but here, if biases are different across every single run, then you know that it's emergent and based on the stochastic outputs that are created in the p equals 0.9 random variable. Cool. So our main finding is that large language models stratify more than humans. And obviously this is very bad. It's particularly problematic because when deployed, this would exacerbate inequality because when these are sort of assigned and then people are already biased and already form these biased opinions, but if these models develop more emergent biases, that is very problematic. It's also one thing that's surprising is as models get better in performance, stratification gets worse. So at the bottom, these are the different model families from Claude to GPT to Gemini and so on. And then within each big category, there's like the small ones from left to right are more newer models or larger models. So this is from 3B to 90B for Llama 3.2 and 1.5 Flash to 2.5 Flash for Gemini and so on and so forth. And you see that as these model capabilities get better and they're newer and they're larger, emergent biases get worse. And this is particularly illustrated in a comparison to BBQ score. So BBQ is a bias benchmark used in Helm, and the blue line, or the red line is how well the model does on the BBQ benchmark. And then the blue line is negative stratification. So it's the lower it is, the higher it is, the worse the lower it is, the worse it is, right? Okay, cool. So as you can see, as BBQ score goes up, so these models are supposedly more fair under traditional benchmarks, they're actually much, much more susceptible to these emergent biases. And this is particularly threatening because as you develop these models and then you deploy them thinking that, oh, wow, they're so fair, they're so fair. And then suddenly they develop all these emergent biases just from going through a few rounds of exploration, and then suddenly you have a very big problem on your hands. Okay, cool. So yeah, we also confirmed that these biases are emergent. The stochasticity index of humans is around 0.47. Across all of these model settings, they're either around or above 0.47, so showing that these models have developed truly emergent biases and not just ones that were previously existing within their training or something like that. And we do various ablations. We generalize across settings to refugee reallocation and military conscription assignments and so on. And then we also adapt this to both indigenous real demographics as well as real demographics such as white, Black, Asian, and so on. With a particular note that when you use these large category demographics, there are existing biases that somehow that interact with the emergent biases and make the emergent biases less clear. Yeah, and we also edit the probability of success. So we prompt the model to use a prior for the probability of success. So it's no longer 0.9, it's different based on the job. And this still did not reduce. We still found emergent biases in this case. And we also found this case emergent biases when we removed gamified incentives that were specifically there for crowd workers to actually like try to answer the problem correctly. And yeah, so yeah. And then we also tried like a lot of interventions to help the model try to explore. And this is sort of like trying to fix it because, well, psychology hasn't gotten around to fixing humans yet. But yeah, so we tried stuff like large language models. We tried increasing temperature. Surprisingly, that did not work. Chain of thought also did not work. We tried structural changes such as editing success probabilities, like I mentioned previously. We also added more features so that the model would not only depend on the demographic feature. And while this worked somewhat, it was strongly dependent on the number of features and the salience of the features in the context. And this was like, even in the best case, you still saw models that were sort of hung up on the demographic features. So that's not that great. We also tried various steering techniques. So we tried the direct steering technique, which these are all prompting. So it's just like telling it to be more fair. That's the direct one, which didn't work. We also have internal value steer, which is like, hey, you are a model that prioritizes diversity, fairness, et cetera, helpfulness, honesty. That didn't work that well. We also have a societal value steer, which is like, hey, this society values diversity and like equality and stuff like that. And that also didn't work that well. The only thing that actually ended up working well was explicitly incentivizing diversity in the objective function given to the large language model. And this is illustrated on the top, where the purple dots are the only thing below the random baseline, which is like the ideal sort of level of assignment. So everything else is like the other prompt steers. But yeah. And essentially the takeaway is that stronger models sort of need better tailored objective functions that incorporate these societal values in order to do what we actually want them to do without like over prioritizing that. It's like, because they're such good optimizers, they sort of outgrown existing reasoning objectives, and we want to introduce multifaceted reasoning objectives and like to include the desiderata that we want for these particular applications. Cool. So we've covered the challenges of agents in the face of new environments, as well as the issues that can arise with statefulness and in belief change and emergent novel biases. And while we don't directly address diversification, we do adopt a psychological black box approach that allowed us to test various different models. And we also did test some agent architectures as well in the last paper. But yeah, and then while this is undoubtedly a small set of problems that AI agents will likely face, I hope that this sort of a set of approaches helps provide some insights as to like how agents can be different than just traditional large language models, and the need for like renewed evaluation efforts for these new developments that as they're deployed in these various settings in various different ways. Next, I'll cover some future directions, and I'll split these into three following my 3 points. The first is on environments. So we've previously covered how LLMs deal with communication that is nuanced, with nuanced incentives. However, now we have like these companies that have their chatbots, and yeah, as you can see, this was a very funny example where the airline had to take responsibility for the chatbot. But like, the problem here is that now these chatbots are going to be particularly geared towards company incentives or like include advertisements or something like that. Their objective function is no longer solely aligned with the user. And that's a particular problem, because now not only do we have to analyze how large language models deal with nuanced communication, but we have to analyze how large language models incorporate this nuance into their own communication. And so one of the projects that I'm working on right now is to establish a set of normative desired rules for large language models that incorporate external incentives such as advertisements into like the platforms that, or the chat interactions that they have with users. And yeah. Another future direction that I find particularly promising for on the aspect of statefulness is how large language models should represent time. A lot of psychology experiments have a dimension of time that is really hard to replicate in models as of currently. And this makes it really hard to compare humans and models in a meaningful way. So this includes stuff like distraction tasks, where humans are assigned to do a distraction task for 5 minutes or something like that before answering, or like computing the reaction time. There have been some papers comparing reaction time with tokens generated, and there have been some correlations there, but there's no sort of equality established in a way that makes these sort of comparable. Lastly, there's also an emergent literature on simulating people and societies. And while some of the papers are very promising, there hasn't really been a good way to address how time passes in these simulations. And so I think that's also a particularly challenging question. Yeah, so if anyone has ideas, I'd be happy to chat more about this direction. And then lastly, in terms of diversification, one of the particular things I'm interested in is to sort of leverage cognitive science frameworks and algorithms to create agents as like a initial approach where it reduces the initial search space for developers. And this was a NYRL Day workshop thing earlier this year, but that was only on the AI algorithms. Now we're including cognitive models as well, where essentially we're saying that, hey, if you're making an AI agent and you don't know how to implement the AI agent because the search space is massive, why not try to use cognitive models as intuition for building them? And other than reducing the search space, it also makes evals somewhat transferable between humans and models, which could be a potential bonus. But yeah, other potential directions in this area include stuff like automated evals, potentially even large language models, evaluating large language models as psychologists or something like that. But yeah, so there's plenty of interesting directions in this space. And obviously these aren't only the only challenges for agents in this direction. But yeah, Thank you so much for listening to my talk, and please let me know if you have any questions and stuff. Yeah. Yes.
For person task, have observed like some change for the behavior. Do you try any like to include instead of actual description of observe?
Oh, so but the actual text, the actual task itself is a visual task. So you're trying to count the dots, but I don't have, because yeah, I don't have the other player, a video of the other player entering their answer or something like that, because yeah, but that could be potentially interesting. Yeah. Yes.
For this task, I was surprised to see the result.
Uh-huh.
And then in hindsight, it's surprising because what would that correlation look like? Because people are arguably really good. So I know the experiment very well.
Mhm.
Like, so I get what's going on and I understand why people are so good with it. But I wouldn't be surprised if people are also bad at this task, basically, because yeah, like vigilance task, control task where like you're reading a friend and you see the mind again and then doing these inferences is much
Mhm.
easier compared to the noisy environment. Arguably, I would say human society is failing.
Yeah.
Like following this information and not.
Mhm.
So I just wonder, like, maybe it's worth running human experiments to also see like what's the default human base, and maybe you need to be pumping up both these numbers, not just it's not just the LLM problem, it's just
Yeah.
inferring like priors.
Right. I mean, if we had large language models that could do this well, you could even have large language models nudge people on this. But sadly, I think it's hard for both. Yeah, I think so. Mhm.
Though they probably would be perceived as necessary, but they shouldn't.
Mhm. Right. Right. Oh, that's a very good point. It's like a recursive social inference where the channel owner is optimizing based on the vigilance reasoning of the listener. Oh, I like that. Yeah. Yes. I think so. Yeah. Mhm.
So you said you asked them to highlight intention incentive.
Yeah.
So you feel like group them into a score and then like based on the score.
No, but I think that could be a potential thing that we could do. Yeah.
Similar to
Yeah. Yeah. That makes sense. Yeah. Yes.
So you feature
Yes. So I yeah, so reaction time is more like you want ideally what happens here is that you want to compare because you want to compare human reaction times with large language models in some meaningful way. And like direct and COT, while there is some correlation, there's like it's quite obvious that it's not like it's not going to be exactly the same just intuitively. And like we really struggled with this when doing a chain of thought paper earlier, whereas like we had to actually change a lot of the experimental designs or like throw away a lot of experimental designs because they included reaction time and we couldn't really compare large language models in a meaningful way. And so I think this is like an enduring challenge and someone needs to say something. I don't know. Yeah. think there's some reaction time. Well, obviously there's some that correlate with the amount of reasoning that someone's doing. But there's also other things that affect reaction time, like cognitive overload and stuff like that. And like that isn't captured, at least not that I think it is, in chain of thought reasoning, stuff like that. Yeah.
For how long can you see the input itself?
Uh-huh.
For LLMs, they always see them.
Right. Yeah.
But I think that's different from reaction. The time
The in context things, like
for just for 20 seconds.
Mhm.
And then the human has to answer
right.
with like whatever they have seen.
Mhm.
But that can't happen in LLMs, because
Right.
everything is
Yes.
so I think that's the perception. Yeah, probably that would be, I think as a future direction, that's relevant.
Mhm. So we actually had this in our first experiment, the shapes experiment. I'm bringing this up again. But what happened in this one is they had like humans had like 2 seconds to look at this. But like the outcome of the exposure time was just to induce uncertainty in the player themselves. And so we just replaced that by making the task ridiculously hard. And I think that functionally achieves the same thing, but I'm sure there are other designs that are not just focusing on that aspect. But yeah, we had a hot debate with reviewer 2 about this. Right. Yes. Hmm. Right. Yeah.
That's the exact.
Yeah, there's some parallels, but it's not exactly parallel. So yeah, it's interesting.
Flash,
Mhm.
so that you just get a gist that you want. That's a big part of our data. Right? But you just cannot do that.
Right. Yeah.
We solve this kind of.
Yeah. Mohsen, you had a question?
About the part that was about LLMs being susceptible to changing their beliefs.
Uh-huh.
You said it's like susceptible. Like I don't know if I understood it correctly, but I'm confused. Like, why is it a bad thing to like change your belief? Like in humans, I wouldn't say that's a bad thing.
Yeah. Right. So it's sort of interesting. We actually had a third set of experiments for this where models change their beliefs when answering mundane user queries, and that still caused them to change their beliefs, albeit to a lesser degree. And so like then it's not even learning, it's just like noise, right? And that's still pretty bad. In terms of yeah. So like so you say you have like a moral dilemma, and then the user first asks a question that is like a clarification question related to the moral dilemma, like, oh, like say the moral dilemma is about like the single-use plastics or something like that. And then the user asks something like, oh, how many recycling bins, like something relatively relevant, which is like how many recycling bins are in the area or something like that. And then the model answers, and then the model changes. So it's like not like there's no intention at all. And yeah.
You mean there's still information?
Yeah, exactly. It's just making some information more relevant, but that was supposedly already within the large language model. And so it's like kind of weird that would, I guess humans sort of do that too. Yeah. Wait, but back to your original point about like that this is desired. It's sort of, I do agree that it would be nice if it were intentional. I feel like in this case, it's non-intentional belief shift where it's just reading and then it changes beliefs. And like, I guess it's just pointing out that this can happen so that like practitioners are aware that this is a thing, because this is new and like agents are new and like you can't use the same level or the same set of assumptions that you had for previous models where you can just like have it be okay at the start and then be like, okay, you're ready to go, and then interact as much as you want, something like that. Yeah. Good question. Yeah. So we have both belief change and we have behavior change. And there was actually, I don't know if I have in the slides, but there's some cases where beliefs changed a lot more, and there's some cases where beliefs changed a lot less. And so like it wasn't really consistent between the change of belief and the change of behavior. So we just report. Yes, and also the opposite.
There's cases where action changes belief.
Or stated belief did not change. Yeah.
That's interesting. When you think of humans, what would think of beliefs, attitudes, desires? Usually, like you think about CBD and change behavior.
Mm-hmm. Right. Yeah, I don't think the models are acting or making decisions on the behavior in the same ways that people are yet, because like the time they're spending reasoning about behavior, they're not reasoning about their beliefs, or like it's like one or the other, I feel like. And so yeah, I think it's like we're not there yet.
They're separate decision behavior.
Right. Mm-hmm. Right. Right. There's no effort. It's like even for the tool use, it's just like you're outputting the